Hello, everyone. My name is Yilun Shang. I'm from the Department of Computer and Information Sciences at Northumbria University. The talk today is about scaled consensus of switched multi-agent systems. So first, I will give you an outline about this talk. I will talk about the background about consensus in multi-agent systems or multi-agent networks. And then I will introduce the problems about scaled consensus. The main results have three elements. So basically, it's about scaled consensus. We talk about asymptotic convergence, and then finite time convergence, and then fixed time convergence. So we have three major results in this talk. And finally, I will give a numerical example to illustrate the theoretical results. And finally, I will draw the conclusion. So about the background about multi-agent systems or multi-agent networks, we will see all these kind of, complicated network system in nature, in engineering, and also social science, and so on and so forth, like, the flocks of birds, school of fishes, a swarm of wolves, bees, and then the UAV, unmanned aerial vehicles, robots, traffic systems. So all these systems, they can be represented by a interconnected, system full of multiple different types of networks. We call this a kind of multi-agent systems. From one single agent to a multi-agents, so the key thing here is, we have three major components that kind of govern the system. So first, we have agent dynamics, okay? So the agent in a multi-agent system, they can be discrete agent, they can be continuous time agent, they have different types of dynamics. They can have, a first order system, second order, even higher order systems, right? And then the distributed rules govern the evolution of the system. You have a feedback rule, different control, distributed control rules, like, an event triggered rules, right? Impulsive rules, all kind of different rules. And you can have the mix of continuous and discrete, rules. So different kind of distributed rules. And nowadays, we also use a lot of machine learning algorithms, right? Now, information flows. So in a network, information can be unidirectional, okay? Directed, right? Directed networks, and sometimes we call it undirected, okay? Directed, undirected, different kind of rules, maybe one hop, two hop, multi-hop rules, right? So all these kind of different elements form the multi-agent systems. They create, kind of emergence of collective behaviors and system effects. And on the left-hand side, you will see a figure. This is about a kind of, IoT, right? So different, network of different components. Multi-agent coordination has many applications, like, in control, estimation, coverage, evolution, and distributed algorithms. So here I just listed the 5 points. For control, we are familiar with the consensus, containment, formation, flocking, altitude synchronization, right? For estimation, we have Kalman filter, localization, data fusion, right? Coverage, we have location or partition, sweep, evasion, pursue, system, and research rescue, especially in the, wireless sensor networks, right? And then the evolution, we have opinion dynamics, social networks, and different distributed rules. Okay, so optimization, okay, distributed optimization, swarm intelligence. So all these systems, they kind of involve the multi-agent coordination. So that's actually a very important research area. So, here, I will just first introduce the simplest case of the consensus system. This is a linear consensus problems. Okay, so in 2007. So here, I introduced both discrete system and the continuous system. So for a continuous system, you will see here, we have xi dot t, right? So this is the derivative of the x. X is the status of a network, especially when you have a communication graph. So here you can see we have 1, 2, 3, 4, 5, 6 dots, right? 6 different nodes or 6 different vertices in a network. And then the arrows between these nodes basically means the direction of the edges. And on each edge, you have the weight, okay, the weight of the edge, like Aij, that's the weight between I and j. So if the network is, undirected, usually we will say Aij equal to Aji. Otherwise, Aij and Aji can be different. So for a continuous system, the simplest case is we just take the first derivative of xi, and then it's equal to Aij xjt minus xit. So that's the difference between xj and xi, and Aij is the weight, right? So you will see if xj is greater than xi, then this derivative will be positive. That means as time goes on, the xi, the status of xi can be kind of increased, right? So you will see locally, each agent has a tendency to, kind of converge to an average of its neighbors, okay? But we don't know on the whole network whether there will be a consensus or not. So that's actually an interesting problem, right? Similarly, in the discrete time case, you will have this kind of iteration, like xit plus 1 is equal to xit plus this term. This term, basically the diffusion term, is the same as the continuous system, right? So Aij xj minus xi, okay? So that's two different systems. We have a continuous system and also the discrete time system. So as I mentioned, so here, this is basically a set of nodes, okay, a set of nodes, or we call a set of agents, n agents, okay? So Aij is a weight, usually it's a non-negative weight. So for the asymptotic consensus, we mean the difference between two agents should converge to 0, okay? Between any two agents, like xi minus xj, it should converge to 0 for any ij belong to V, belong to the set of the nodes, right? And also this should hold for any initial conditions. So this is called basically a asymptotic consensus. As time goes to infinity, the difference, okay, the gaps will reach 0, okay, asymptotically reach 0. So that's the simplest case, okay, the simplest case. And we can have a kind of generalization to consider the scaled consensus, okay? So basically, what is scaled consensus? So here, we will introduce some non-zero scalars. Basically, that's real numbers. They can be positive, they can be negative, okay? So S1, S2, S3, Sn, right? So asymptotic scaled consensus with respect to S1, Sn, that means here we will multiply the status xi by Si. So Si, Xi minus sjxj, they should converge to 0 as time t goes to infinity. This should hold for all the nodes, okay, for all these agents in the network. So that means, the scaled value will converge to the same value, right? The scaled value of the agents will converge to a common value, okay? That is why the discrepancy decreases. Basically, they will disappear, right? So multi-scaled is a kind of multi-scale, this coordination control actually have many applications, like in social media, in the opinion networks, okay? So different people have different opinions, so they may not converge to the same final result, but the scaled value may be converged to the same. And also in the space vehicle and the moderation, the space vehicle and the wireless communication with respect to the grounding vehicles, so on the sky, in the sky, basically the scales are very large, like thousands kilometers, but on the ground, basically the interaction between robots is just within meters, right? So they have huge difference in terms of the scales. So if we can set the scale Si, then, we can easily, model the whole system into one framework. So scaled consensus actually have a practical interest, okay? So here we will introduce the so-called switched multi-agent system. So as I just mentioned, for agent dynamics, they can be continuous time and discrete time. So here we will try to combine them, okay, to create a switched system. So for a switched multi-agent system, it has basically two components. One component is called the continuous time subsystem. So like this, xi dot equal to ui. And then another component is about the discrete time subsystem. So this is the iteration system, right? So xit plus 1 equal to xit plus h times uit. So h here is the control gain, okay? H is a control gain, usually positive and small, right? So uit again is input, control input, okay, the control input. So we have a mixed system. So here, switch system means, you know, synchronous switch for all the agents, okay? So all these agents update, okay? All these agents update synchronously through across the whole network, okay? So it is important that we can find out a switch rule. How can we, you know, switch between the first system and second system? You know, how do we switch between the continuous and discrete time systems so that the consensus can be reached? So this is a kind of complicated problem. So next we will introduce our main results. Okay, so the first result is about asymptotical convergence. So you still remember, for asymptotical convergence, basically it means the discrepancy between the xi, xj, or maybe si, xi, and sj, xj, the difference will converge to zero as time goes on, right? So now we here consider the switched multi-agent system. Again, so for switched, we mean we have a discrete time component, and then we have a continuous time component. Okay, it's like this: xi dot t equal to ui. This is a continuous time system. And then we have a discrete time system, xit plus 1 equal to xit plus hui, okay? And then here we specify the ui. So this is the key part, right? We needed to design the ui so that the system reach consensus. So this is the main point of this theorem. So we needed to introduce a suitable ui. So here, this is how I designed this ui. So uit is equal to sgn si. So sgn here means the sign of si, okay? That's the sign. That means if si is positive, the sgn is positive 1. If si is 0, the sign is of course 0. If si is negative, the sign is negative 1. Okay, so that's the sign basically. And then times sigma from i equal to 1 to n aij si xj minus si xi. So this is basically similar like the original one. So the key point here is we will design the we'll have this sign in front of the diffusion term. Okay, now let dj means in degree of node I. Okay, so that's take the sum over all I. Okay, take the sum of all these I. So this is the weighted degree. Now, the first theorem 1, read like this. So suppose that's the communication graph. Okay, suppose the underlying communication network is strongly connected. That means, you know, any two nodes has a directed path. Okay, so they are interconnected. So if h times si, the absolute value of si and di is less than 1, so that means if the control gain is small enough, right? If the h is small enough, then we can conclude the switched multi-agent system, this 1 and 2, okay, the switched multi-agent system can achieve asymptotic scaled consensus with respect to these scalars S1, S2 to Sn under any switching law. So this is a kind of very strong result because it guarantees the consensus, okay, guarantees that asymptotic scaled consensus with respect to the Si to Sn under any switching law. That means, you know, however you switch these two components of the system, the consensus will always hold. Okay, it doesn't matter how you switch the system, the consensus result always hold. So this is for the theorem one about asymptotic. And then we have the finite time consensus. So what does it mean? What does that mean? The finite time. So again, we have these scalars from S1 to Sn. Okay, so finite time scaled consensus with respect to S1 to Sn. That means, you know, it will reach 0. Okay, the discrepancy between these scaled status will reach 0 if t tends to some fixed time. Okay, tends to some fixed time. So here, this capital T x0, that means, you know, this is a finite time. Okay, this is a finite time. So as long as t tends to this finite time, the consensus will be reached exactly. Okay, the consensus will be reached exactly. So that means, you know, if t is greater than or equal to this time, then the equality holds. Okay, the equality holds. So that is much stronger than the asymptotic, because in the asymptotic case, you may reach consensus, but it can take a long time. Okay, it can take infinite time, right? But here we only use finite time, and then we can reach consensus. So this is much coveted in many applications. Okay, so here again, tx0. That means, you know, this is a finite time t, but this time t can depend on the initial you know, configuration of the system. It depends on the initial condition of the network. So it depends on x0. So we put x0 in the parentheses here. That means t depends on x0. But anyway, this is a finite time because x0 is a fixed number, right? Set of fixed number. So anyway, this is a finite time. Okay. So again, for this system, we consider the switch system like this: xi dot t equal to ui. That's for the continuous one, and then for the discrete one, similarly, we have the same system basically. So the important thing is we will design the protocol. Okay, we'll design the protocol. So here, this is our UIT. So UIT, you will see for discrete system and for continuous system, we have two kinds of different, control rules. But basically, if you read that, you will see it's kind of similar. We still have the sign, okay, the sign function here. Again, we have the sign function inside the sigma, okay, and then we have the Bij as a power, okay. So here, Bij equal to Bji, it's a number between 0 and 1. So our second theorem about finite scaled consensus reads like this. Again, suppose the network is strongly connected, okay? The network is strongly connected. We have a directed underlying topology, but it is strongly connected, okay? So we can say, as long as we use this control rule, okay, the UIT, we will see that the switched multi-agent system can reach the finite time scaled consensus with respect to S1, Sn. Again, that is under any switching law, okay? That is under any switching. So you will see all these theorems of the same flavor, okay? So they can reach consensus under any switching rule, okay? It doesn't matter how you switch the discrete system and the continuous system, you will always reach the consensus, okay? You will always reach a consensus. But the key thing here is how we design the UIT, how we design the input, okay, the feedback input. So here, this is the main result, okay? This is the main result. Moreover, we can tell the reader basically, as I said here, you will see we have a finite time t, this capital T. We can actually, in this theorem, we can determine this t, okay? We can find out this t. So this t here, we use t star, okay? We use t star. So the formula is kind of, you will see it's kind of complicated, but if you look into this formula, you will see as long as you know the initial condition of the system, and also you know the network, the topology, you can calculate all these different terms. You will see we have the things like, rho 1, rho 2. So what is rho 1, rho 2? You can calculate by using this formula, okay? Rho 1 is a positive number, rho 2 is also a positive number, okay? It depends on a matrix B, the Laplace of a matrix B. So what is the matrix B here? This is the Bij, you remember? The Bij basically is, the power in the feedback rule, right? So we will design this Bij, okay? So these are not any Bij. We have to design particularly in this way, okay? You have to design this Bij particularly in this way. That's xi absolute value times Aij and then the power of this, okay? And then you will see we have a V0, okay? We have a term V0. So what is V0? V0 is given by this formula, okay? It's given by this formula. So as I said, if you have initial conditions, initial configuration of the network and system, you can easily calculate the T star, okay? You can easily calculate T star. That means when you have a real system, you can determine how much time it will take to reach the scaled consensus. So that's very handy, right? You can calculate this T star actually by using this formula, okay? Now our last result is about a fixed time convergence, a fixed time scaled consensus. So what's the difference between fixed time and finite time? So here, the major difference is, here you will see this T, this capital T, it does not depend on the initial condition. You remember in the finite time case, this T depends on the initial condition, okay? So that means if you change the condition, if you change the initial configuration, and the time to the settling time will change. But here, for the fixed time consensus, it will not change. It is a fixed number. It does not depend on the initial condition. Again, this is even stronger than the finite time. It does not depend on the initial condition, okay? So result is kind of similar. So again, we consider this switched multi-agent system. We have the discrete system, and then we have another continuous system. Now this time we will design the UIT like this, okay? We will design the UIT like this. You will see here for the discrete time, we have two components, okay? So this one and plus this one. Okay, we have two components, and for these components, we have different power, okay? We have m over n, and then p over q. Here, m and pq, they are positive odd integers satisfying a relationship like m greater than n, p less than q. So any number, m and pq, as long as they satisfy this condition, we can use them as a power, okay? So it's kind of a little bit, flexibility here. So we have this flexibility, and then The final result, again, is similar, okay? Suppose the network is strongly connected and H is not too large, then we can reach the fixed time scaled consensus, okay, under any switching rule, under any switching law. Again, similarly, we can determine this fixed time t. So here you will see the t hat is this fixed time, right? This is fixed time. Similarly, we will kind of, calculate this row 1 hat, row 2 hat, and all this matrix, and do the kind of optimization. But all this can be done easily because in real networks, in real multi-agent system, multi-agent networks, the network is not too large, right? So this matrix is not too large. So all this can be calculated very quickly. Okay, they can be calculated very quickly. So anyway, you can find out the t hat. So the key thing here is you will see the t hat does not depend on x0. It no longer depends on x0, right? So it is a fixed time. Okay, it is a fixed time. So this is called fixed time convergence or fixed time scaled consensus. Okay, it does not relate to x0. So that's the key point. Okay, that's the key point. But of course, you will see the design. You have already seen the design is actually a little bit complicated because here we have m and n and p and q. We have 4 integers to specify the power of the feedback rule. So it's a little bit complicated than the original, the finite time or asymptotic case. So it's a little bit difficult, but the result is stronger, right? The result is stronger here. Okay, so that's about these 3 results: asymptotic consensus, okay, the finite, and the fixed time. So next, I will give a quick numerical example. So here we consider a communication graph with n equal to 4 agents, right? We have 4 agents, 1, 2, 3, 4, and you will see we have some arrows between them. So you can easily check, and this is a strongly connected network, okay? Any 2 points, they have a directed path, right? This is strongly connected network. And then each edge has a weight, okay? Here currently is 0.1. And then we can specify these numbers, okay? So 0.5, m equals 7, n equal to 5, p equal to 3, q equal to 5, and h takes 0.1. So with this setting, you can easily check the conditions of these theorems, theorem 1, 2, 3, they all hold, okay? So all these conditions hold. So we will get the consensus as expected. So let's see. Here, I use the switching rule like this, okay? So the switching rule is like this one, okay? So that means, 10 minutes or 10 seconds for the continuous, and then 10 seconds for the discrete system, and another 10 seconds for the continuous system, another 10 seconds for the discrete. So the periodic kind of signal, right? So they switch between continuous component and then discrete component. So we have 3 figures, okay? Here, the figure B here on the top right-hand side, you will see the asymptotic scaled consensus. So that's the trajectory of these 4 agents. So you will see they reach scaled consensus. They actually reach scaled consensus. So if I go back to the previous slide, you will see S1, S2, S3, S4. That's 2, 1, 1, minus 1. So remember, that's 2, 1, 1, minus 1. So now if you look at the final results, okay, if you look at the final results, you will see, for example, this magnet one is about 2 times this, minus 2 times this red one, okay? And then this blue one is about 2 times of the red one. So that they actually reach the scaled consensus. You can easily check by using the formula, okay? So Si, Xi minus Sj, Xj tends to 0, okay? So in this case, this is a symptotic convergence. And then at the bottom left corner, you will see this is a finite time consensus, okay? Finite time consensus. Again, it reached consensus in finite time, So it reached consensus, but it reached consensus finite time. So if you see the trajectory is slightly different, and the convergence is actually, I think it's actually quicker than the asymptotic case. And then at the bottom right-hand side, you will see the finite time scale consensus. In this case, the consensus scaled consensus will be reached in finite time, okay? It will be reached in finite time. So you will see the consensus actually speed is even faster, okay? The speed even faster. So that's basically a very simple example. So our conclusion here is we propose 3 scaled consensus protocols with 3 different consensus rates, right? Convergence rates for the switched multi-agent system containing both continuous and discrete system, and the settling time can be decided for fixed time and also for finite time consensus. And then we can even generalize to formation control problems. Okay, so thank you very much for listening.